So for our concept, we chose Ohm's law, which Ohm's law is V equals IR, where V is the voltage, I is the current, and R is the resistance.
Alright, so voltage itself is the electromotive force between electrons via the positive and negative charges in a circuit. And so the current itself is the actual movement of electrons, and whereas the resistance is what the current flows through, the value of the resistance is how hard it is for a current to flow through this.
Here you can see a normal circuit with a voltage source, a resistor, and a current that flows through the circuit. Now, you can think of a circuit kind of like a pipeline, where current is the water flow through a pipe, and the resistance is the size of the pipe. The higher the resistance, the lower the current flow through the pipe. This can be seen through the relationship as well by rearranging V equals IR to I equals V over R, as it is an inverse relationship between resistance and current.
And to physically show this representation, we are going to show this via two circuits. Our first trial is going to test this portion of the Ohm's law. Rather, we're going to hook up a voltage source, fixed voltage source with DC current, which means it has a direct current that has a maintained voltage which will not change. We're going to hook that up to a resistor, which will always have a constant resistance, and we'll measure the current, which should be the voltage divided by the resistance. So in our first trial, what we used was a constant voltage source of 5 volts, and we used different resistors in separate trials where we hooked up the 5 volts to each resistor and measured each current. Using the an ammeter, we were able to break apart the circuit and analyze the current flowing through the circuit itself from the voltage source through the resistor. So with the results of our first trial, we verified that Ohm's law did in fact work with the equation V equals IR, since our findings were close enough to our calculated values. And in our second trial, we did a visual representation of this where we used two different resistors each trial. The one who had the larger resistance would have a smaller current according to Ohm's law, which means with less current flowing into a LED means that there would be less light being emitted from the LEDs.
So for our Ohm's law application, we chose battery chargers. So since the invention of batteries, at least rechargeable battery chargers have been important, obviously. So especially in today's world, people are in big hurries and they're always concerned about how much time they're having to wait for their devices to be charged, whether it be their laptops, their iPhones or other phones, or their iPads, anything. People are on the go, but we're also on our devices all the time. So however fast that battery charges is very important to consumers. Engineers at multiple companies have seen this, and that is why they have put an emphasis on making chargers that charge their devices very quickly. You'll actually see that that's one of the main things that a company will advertise about their product is how fast you can get to 50% or to 100% battery charge. So when engineers are looking into this problem, they actually go way back to the roots and look at Ohm's law. It's one of the quickest ways to decrease your charging time. So if you look at Ohm's law, you'll notice that if you lower your resistance, you increase your current. So by lowering that resistance in a battery charger, you increase the current going to the phone, which increases the amount of flow of electrons into that phone, which will make it charge significantly faster depending upon how much you reduce the resistance. Engineers are getting a lot better at it, and that's why you'll see that a lot of new technology can charge pretty quickly. And this just by lowering the resistance is the main way. So that is why Ohm's law should always be kept in consideration even when tackling these big problems, because it's still a very useful tool.